So welcome back. We're now going to talk specifically about the statistics that we use when we're talking about quantitative psychology and quantitative research in IO psychology. This is basically just kind of a brief review, and the main reason we're going through this is I will be using a lot of the terms that we're going to talk about in the next 10 or 12 slides in a lot of the other lectures, and I want to make sure that we're all on the same page as far as this goes. So when we're looking at data analysis, the first thing that we talk about is descriptive statistics. So again, this is focused on purely quantitative. So when we're using quantitative methods, we are using a reliable and valid measure to try to look for patterns and relationships and to also just describe what's going on. We're often going to start with descriptive statistics. They summarize, they organize, and they describe a sample of data. They basically allow us to talk about data in a very summative way. So the first thing we'll often look at is a frequency distribution. So for instance, if I was measuring job satisfaction in an organization, I have about 100 employees and all I do is give them a scale of job satisfaction, a 5-item scale they fill out, and I average their score. At that point, the horizontal axis on the normal distribution that's shown below on this slide is the scores running from lowest to highest. So if you had a very low score, you would be on the horizontal axis to the far left. If you had a very high score, you'd be on the horizontal axis to the far right. The vertical axis indicates the frequency of occurrence. And we find that in most things that we measure in IO psychology, we find these normal distributions. So generally speaking, if I go into an organization and measure job satisfaction, I'm going to find very few people that are truly despising their job. No job satisfaction whatsoever. But there's probably not a whole lot of people that love their job above and beyond everything else. Most people are going to fall somewhere in between, and that's what we find with normal distributions. A small number of very low scores, a small number of very high scores, and most people, generally speaking, about 60 to 70% of people falling in that middle range. So once we have that distribution, we now want to talk about how we can define that distribution in just a few terms. And generally what we want is two key terms. We want a measure of central tendency and a measure of variability. So the measures of central tendency are mean, mode, and median. In a normal distribution, in other words, a symmetrical distribution like was on the previous slide, where basically you could cut it in half and fold it over and it would look very similar. The mean, the mode, and the median are always going to be very similar numbers. So the mean is just the mathematical average. If you had 10 scores, you would add them up. Score 1 plus score 2 plus score 3 plus score 4, etc., all the way up to 10. And then you divide by the number of scores. That gives you the mathematical mean. Mode is just the most common score. And median is that if you placed the actual scores on a line from lowest to highest, what is literally the middle number. The next thing that we look at, once we actually know what the center of the distribution likes, in other words, the center is telling us what is the average score, we also want to know how much variance there was off of that average score. And this is variability. And there's a couple ways to measure it. Range simply is the smallest score to the lowest score. So if I measured job satisfaction and the lowest job satisfaction I found was a 2, and the highest job satisfaction I had was a 7, my range would be 2 to 7. We can also calculate variance. Variance is simply taking every individual score minus the mean of that sample, squared, added up, and divided by n. So anytime you see sigma, that's that little weird-looking backwards E guy there, that simply means just do this for every single score and add it up. So every single score minus the mean of the distribution squared, add those all up, and then divide by the total number of scores gives you variance. A slightly different equation gives us actually what's often referred to as standard deviation, SD or S. And it's the square root of variance. So notice the equation is almost identical, with the exception that at the end we're taking the square root. Also notice I changed n to n minus 1. This is basically just an acceptance that we want to be a little careful when we're estimating error. So it's a mathematical adjustment to make us a little more confident of the number that we're generating. So if we have a normal distribution, the first thing we know about it is that the mean, the mode, and the median are all the same. The second thing that we know about it is that if we have a normal distribution, based on that mean, once we've calculated a standard deviation, those two numbers tell us an awful lot about that distribution. So in a normal distribution, the mean, the median, and the mode are equal. And also, 68% of scores, on average, will fall within plus or minus 1 standard deviation from the mean. So for instance, if we have an intelligence test, most intelligence tests are normed, or they're created specifically to score that the average score on an intelligence test or a cognitive ability test is 100. And the standard deviation is 15. So what that tells us is that if we knew that it's a normal distribution, then if someone has, with the middle mean score is 100, that means that approximately 68% of people fall between 100 minus 15, 85, and 100 plus 15, 115. So 68% of the people in the world have an IQ between 85 and 115. 96% of the people in the world fall between plus or minus 2 standard deviations, so between 70 and 130. So if your IQ is below 70, you're in a pretty small group, and if your IQ is above 130, you're in a pretty small group. So once we know that we have normality and those assumptions of normality, then we can talk a lot about what's going on in a distribution without ever actually seeing the individual scores. All we need to know is the mean and the standard deviation to start to be able to put into perspective individual people's scores. So if someone told me their IQ or cognitive ability test was a 145, I know, based on that information of the mean is 100 and the standard deviation of 15, that person is a very smart person compared to most people. Now, all of our statistics that we're going to talk about in this class, if we're talking about a measure of anything that's continuous data simply refers to the numbers have meaning and they have approximately equal distance from each other. And those are the kind of data that creates these normal distributions. That all of our statistics assume normality. They assume we have a normal distribution, that it's symmetrical, and that this mean and standard deviation rule of 68% and 96% is being met. So we do need to check for normality, because if we have data that's non-normal, we can't really look at it with the same way. We can't do advanced statistical analysis on it. So there's a couple of problems that can come up with. The first one is called kurtosis. Kurtosis is simply the extent that a distribution is flatter or more peaked than a normal distribution. Platykurtic is shown in blue there. So a platykurtic distribution is a very flat distribution. And the problem with this is it's still symmetrical, so it's still somewhat normal. But the problem here is that it's no longer to where most people are scoring in the middle. In fact, people are scoring all over, from the very lowest score to the very highest score, across that distribution. A leptokurtic distribution, again, it very likely is normally distributed as far as if it's symmetrical or not. It just means that everyone is lumped up very close around that mean. So the problem with this often is not necessarily that there's a problem when you have a leptokurtic distribution. The problem occurs is when you're trying to compare two groups and they have different levels of kurtosis. So if you're comparing the mean of a group with, let's just take a look at this, the graph right to the right of the slide. So we have two distributions, one in red and one in blue. If we look at the center point of both distributions, it's the same. So if we were making a scientific experiment where we were looking for mean differences with a statistical analysis, we would say there is no difference between these two groups. And that is inaccurate. In reality, there's a large difference between these groups, but it's not a difference in their means, it's a difference in the shape of the distribution. Our statistical techniques are not designed to look for shape difference. They're designed to look for mean difference. So when we have this, it's a deviation from normality, and it's a problem for statistical analysis. A bigger problem is skewed distributions, because it's no longer the shape of the distribution, it's the fact the distribution isn't normal anymore. So a positive skew is there on the left, and it refers to when our distribution actually has a fair amount of numbers with very high positive extreme scores. And then on the right is an example of a negative skew, where there's quite a few people that have a very low score. Now, the problem with either of these distributions is, again, our assumption of normality is that the mean is the center of the distribution, and that half of the people score above the mean and half score below the mean. But because the mean is calculated by just mathematically averaging all the scores, if you have some extremely positive scores, those positive scores are going to drag the mean towards them. So looking at the example on the left, you can see that the mean now has been dragged towards those extreme positive scores. The median is not as affected because we just put the scores in order, so it doesn't care the size of those positive scores, but it still moved a little bit. And the mode is the only thing we can trust in a positive or negative skew. Because remember, all mode is the most common score. So it is always going to be at the top of the arc of the distribution. But even the mode is, none of these are useful as far as being able to split that distribution into a top half and a bottom half, low scores and high scores. So if we look at the mean, again looking at the positive skew, you can see that probably a good 2/3 of people actually score under the mean, and less than 1/3 score above the mean. Again, our statistical tests assume that we have symmetrical distributions, that the mean is the center point of that distribution, that the mean is equal to the median in the mode, and that distribution there's an equal number of people below the mean as above the mean. So if we have a normal distribution, we can then use inferential statistics to start making comparisons of those means. So it aids in testing hypotheses and making inferences from sample data to larger data. So what that actually means is that inferential statistics aren't just about calculating whether there's a meaningful difference between two groups based on their mean score on an outcome. So we measure performance between two companies, and we find that one company has higher performance. That's a statistical test, but the inferential part is that a part of these statistics is also a calculation to determine external validity. How likely it is that once we find a difference, that difference would be found in new populations or new groups. So inferential statistics include t-tests, f-tests, chi-square tests, correlations, regressions. And a major part of this is we get two pieces of information with any inferential test. We get the test itself, and that test tells us, is this particular difference or pattern meaningful? But we also get statistical significance, a p-value. And that's a probability statement. That's not a test effect. That's not an effect size. A lot of people get confused about that and think that p-value or statistical significance is how big the effect is or how important the effect is. It absolutely is not. Statistical significance has nothing to do with effect size directly. It's not about whether you found a difference between groups. That's the test statistic. That's the t-test. That's the f-test. That's the correlation value. The statistical significance calculation, the second thing we're calculating with any inferential statistic, is a probability statement that states how likely is it that we would find this effect in new samples. It is literally a measurement of external validity. The threshold for significance is set at 0.05 in industrial organizational psychology, and that represents a probability, 5%. We're willing to accept a result that we find as long as there's a 5% or less chance that we wouldn't find it in new samples. So the terms alpha refers to that 0.05. Alpha is always 0.05. Alpha refers to our threshold of significance. P-value changes from study to study to study, and that's the actual calculated value that we want to see be below 0.05. And if it is, we claim statistical significance. Statistical power is the likelihood of actually finding a statistically significant difference when a true difference actually exists. And there's a couple of things researchers can do to try to increase the chances of them finding statistically significant results. So I have here 3 examples of things that actually reduce power, and then therefore also the reverse of them would increase power. The smaller the sample size, the less likely you are to find differences. The lower the alpha, so the less likely you are to be willing to accept being wrong, the harder it is to find differences. And finally, the smaller the actual effect is, the smaller the likelihood of finding a true difference. So a researcher can at least basically use 2 of these 3 to their advantage. So the second one, lowering the alpha. Remember, alpha is that 0.05. It's the marker that we set for our acceptance of statistical significance. You really can't move that. If you could, you would be able to make your studies more powerful. If you were willing to accept a 10% chance of being wrong, you could actually make a claim of statistical significance with smaller test effects. What we can affect is the sample size and the actual effect size in our studies. So the more people you have in the study, the more power you have, the more likely you are to find a difference. And again, the reason for that is, remember that what we're calculating here with statistical significance is the likelihood that what we find in a group would be found in other groups. So thus, the larger the group is that you tested, the more easy it is for us to say that a difference we found in that group would be found in new, different people, because we've got a larger group of people that we tested in the first place. And finally, the actual effect size. So let's go back to what I was talking about in the previous module for this set of the third lecture, and that was my study looking at Slayer versus Lady Gaga. Compare that to a study that actually looked at just two different types of very similar music. Half the group got to listen to a song from Megadeth, and the other half of the group got to listen to a song from Metallica. At that point, that would be probably, if there is a difference in those two types of music, it's probably going to be a very small and subtle difference. Very less likely that we'd find a difference. In other words, it's got a small effect to begin with. It's going to be hard to find that difference and to be able to claim that we'd find that difference elsewhere. That's why a lot of times, especially in early experimental designs, when we're just starting to look at something, we'll often try to make sure we're looking at two very different situations. So instead of like comparing a 2-page study guide versus a 1.5-page study guide, compare a study guide to no study guide. Very big differences. And then if you find that difference, additional studies could look to see at what levels or what little incremental differences in study guides still have a findable effect. So, a lot of what industrial psychology, organizational psychology uses as far as statistical analysis is the correlation. So I do want to briefly talk about correlations, and we're going to be looking at correlation displays throughout this class. So a scatter plot is basically a display that shows a correlational relationship between two continuous variables. So in this case, I've got training grade on the vertical axis going from 0 to 100, and I've got a cognitive test score going from 0 to 100. Each dot on this graph represents one person's score on both of those tests. And we see a positive linear correlation. People with very high cognitive ability, on average, tended to score fairly high on the training test. Those with very low cognitive ability tended to also score lower on the actual training grade. So regressions are correlation and regression. So the only difference between a correlation and a regression simply means we're also going to try to predict with the exact same information. So correlations and regressions both look for patterns in data, patterns in continuous data. So pay by job satisfaction, that would be a correlation. Job satisfaction by performance. If performance is being measured on a 0 to 10 chart, that would be a correlation. If we also want to try to predict future performance by measuring new people's job satisfaction, that would be a regression. So we call it a regression when we're also wanting to predict. We call it a correlation when all we're doing is looking for the pattern. So a couple of things about the regression. The regression produces a correlation coefficient. That's the test score. Again, that's not the p-value. That's the actual test of how big is the effect. And that's generally referred to as Pearson's R. And what it represents is a straight line that best fits that scatter plot of data. So it's a statistical measurement of association, Pearson's R. The actual number represents the magnitude. So the absolute value, and Pearson's R ranges from 0 to -1 to +1. So -1 through 0 to +1. So you'll never have a Pearson's R of more than 1.0 or -1.0. And that represents percentage. So a Pearson's R of 1% means, or 1.0 is 100%. Those two variables predict each other, are 100% related with no error whatsoever. Now we're rarely going to find that in any real kind of measurement, but that represents the upper and lower limits. That number represents the actual magnitude of the relationship. The larger the number, the stronger the relationship. And -0.9 is the same strength as +0.9. So the sign, the direction, positive or negative, is not an actual value statement. It's a direction statement. It tells us the direction of the relationship. And I'll go through some examples in the very next slide. If we're actually interested in the exact percentage of shared variance, we need to actually square R. So the effect size of a correlation or regression, an estimate of how much variance is being explained, is simply squaring that R. So, for example, if we found an R of 0.10, it actually is only representing 1%. 0.10 times 0.10 is 0.01, 1%. an R of 0.40. So 0.4 times 0.4 is 0.16, 16%. 1.0 times 1.0 is 1.0, 100%. We can also look at multiple correlations, and we can look at multiple predictors' relationships with outcomes. But overall, what we're always looking for is the linear association between our predictors, even if it's several predictors, and some form of outcome. So here's some just examples of correlations. A positive correlation is shown in the middle. As one variable increases, so does the other. A negative correlation is shown to the far right. As one variable increases, the other one decreases. And I want you to note that, take a look at these two correlations. Again, looking at the middle and the right. Both of them have an R of 0.50. In other words, and again, an R square, 0.5 times 0.5, of 0.25. So the R squared is 25% of the variance in one variable is being predicted by the other. And that's pretty good. You can take a look at these correlations and go, if you knew someone scored fairly high on the horizontal axis, you can pretty much guess that they're going to score relatively high on the vertical axis, whether that's cognitive ability by performance or whatever you're measuring. The relationship, the strength of that relationship is the same in both the middle and the right. It's simply whether it's a positive relationship or a negative relationship. If your R is 0 or close to 0, it usually represents no relationship. So you really can't predict one score from the other. Now, it is also important the assumptions of the correlation. The correlation has an assumption of a linear relationship, that the best way to describe that scatter plot is going to be a straight line. However, you can only assume that you're actually accurately using a correlation if it is linear. So we often have to look at the scatter plots. So for example, here I have a curvilinear relationship. And this is a very common finding in human performance. So this is based on real-world studies and data. And that is that our amount of arousal is positively related to performance up to a point where it becomes then negative related. So basically, looking at the horizontal axis of stimulation or arousal, if you are absolutely bored and you're sleepy, you really don't care about anything, you're not aroused and you don't care, your performance is going to be very sloppy. As you become more aware, more alert, more sharp, your performance is going to increase. But as you become more and more stimulated, more and more aroused, you're going to become jittery, you're going to become anxious, you're going to become worried, you're going to become aware of other people watching you, maybe judging you, and your performance is going to go down. The problem is this is a very strong relationship, and it's found in a lot of areas. But if we tried to run a correlation with it, all those dots would average out to a straight line, a correlation of 0, no relationship. So to be able to trust correlations, we also have to know to check those scatter plots to make sure it's a linear relationship to begin with. The final statistical technique I want to talk about that we use a lot in IO psychology is meta-analysis. It's a statistical method for combining results from many studies to draw a general conclusion. The idea here is that instead of studying individuals by bringing them into an experiment, we're going to actually study studies. So a meta-analysis, for instance, might look at 50 studies that have all looked at job satisfaction, combine the results of all 50 of those studies into one massive study, generally focused on the idea of external validity. In other words, across all of these studies, do we consistently find that job satisfaction is related, for example, with performance? So meta-analyses are commonly used in IO psychology to draw from all these individual studies. A study done at a manufacturing plant in Detroit, a study done at a university in Texas, a study done at a consulting firm in San Francisco. And looking, okay, we've got job satisfaction related to performance in all these studies in many different settings, different places, different jobs, different people. If we find that when we combine all those studies together, we still find a statistically significant, strong effect, we've got even more evidence that this is a meaningful difference that we should be acting on, and we should be changing our workplaces to help. Another thing we can use with meta-analysis is we can also look for differences between the studies. We often refer to these as statistical artifacts. There are characteristics of particular studies that might distort the result, but it might also give us information of where it works and doesn't work. So, for example, a meta-analysis might very well find that studies of job satisfaction and performance are strongest when they're done in experimental conditions at universities. They're fairly strong with fairly direct and simplistic jobs, often factory jobs or manual labor jobs, and they're weakest at very complex jobs. Now, that is an example I've just thrown out. I don't have data in front of me, but it wouldn't surprise me, and a lot of times meta-analysis do find that the strongest effects are usually in controlled settings because the experimenters are being able to control everything, including the level of the manipulations. And they've probably got a large sample, and they probably have made sure that their manipulations, their effect size, are very strong so that they can find the effects. And when you then take those studies out into field settings where, one, you have less control, but two, a lot of times you don't have as much control even on how you're manipulating job satisfaction, the results become weaker. Also, meta-analysis can examine the differences between sample sizes for different studies. So definitely let me know if you have any questions. The discussion board is always open. There's, of course, the readings that go along with this lecture. And as always, don't forget that there is a quiz due, as there is at the end of each lecture. And I look forward to talking to you the next time you log in and listen to one of my lectures.